Hello, this is the Metropolitan State University of Denver Control System Analysis final project for fall 2014. I'm Michael Denson, and my partners are Ryan Halgren and Andrew O'Donnell. All right, a little background about the project objectives we were given. So basically, we were to design and verify a control system, just any control system we decided upon. A few parameters or guidelines for that was it had to be complex enough, so it had to be at least third order or higher. We were also supposed to include some type of PID controller and some type of lead and lag compensators. When we were designing the system, we were supposed to just come up with a few parameters that we would design the system around, such as rise time and settling time. And finally, the system in the end had to be stable. So after taking into account all the guidelines and objectives we're supposed to accomplish with this project, we decided to design an airplane wing flap control system. So we started with this design that you see here. That top block diagram is the simpler one. It starts on the left with the command coming in and just goes to a controller, a few controllers, and it has some feedback from a tachometer and then out to our load, and then another control loop feedback. And if you go down to the bottom block diagram, the more in-depth one, you start on the left with your input signal, and then you have the first three blocks there would be your controllers, and then the next three would be our motor or model of our motor and how it affects our system. We have a few feedback loops from there after the motor. The one on top would be our back EMF that you see from your motor. The one on the bottom would be the tachometer, that KT. And then if you go to the right from there, it's just another model of our load out from there. And then another control feedback loop back to the input. And what we want to do with this system was, first of all, to simplify it. We found that some of these feedback loops weren't exactly necessary, so we figured we could get rid of them, make the circuit a little simpler, as well as make our transfer function a bit simpler. And another thing we wanted to do was just to add a disturbance, just to model how the wing sees the air, or sees air resistance when it's trying to move the flap.
And you can see here our new modified block diagram with no disturbance added yet. In the beginning we have KS and KT for our proportional and derivative controllers. We kept the tachometer, which shows the speed of the motor, and the back EMF feedback loop, which shows the electromagnetic field produced by the motor. Below the block diagram, you can see our transfer function, with theta y over theta r as our input over output. On the denominator of our transfer function, you can see that the x times 10 to the negative 7th times x cubed gives us the third order system response. And on this slide, you can see our new block diagram with the added disturbance after the motor to model the wind resistance that the plane will see. The value for our disturbance is the 1 over jts squared plus beta ts that you see in the block underneath the motor. And below the block diagram, you see our new transfer function with the output with respect to the disturbance. As you can see on the denominator, we still have the s cubed term, keeping it a third order system.
Here we can see a graphed MATLAB of the step response of our original transfer functions with the KT and KS values set to 1 and 0 respectively. On the x-axis we have our time in seconds, and on the y-axis we have the amplitude. From the graph we can see that the response of our system rises at a pretty good rate, but our settling time takes about 6 seconds, which is not very good considering we're dealing with a control fin for an airplane. Here we took the Bodie plot on MATLAB with the same no KT and KS values for just a default response. The top graph is the magnitude of our system, which has a pretty good decibel ratings, while below is our phase in degrees with respect to the frequency in radians per second. We have a very good graph here with good response times all the way across the board.
Next we have our calculations for KT. The calculation for KT was based on the settling time, which is TS. We decided we wanted our settling time to be 0.5 seconds. The other thing that helps us determine our KT value is the 2 zeta omega n value, which we got from our transfer function to be 10.163 plus 9 KT. From this equation, we can see that our zeta omega n is equal to 9.2 seconds. Plugging this back into our first equation, we find that KT is equal to 0.915. The KT is our derivative value for our control. For the Ks calculation, it is dependent on the rise time of the system. We chose our rise time to be 0.2 seconds. Ks can be calculated by setting omega n squared equal to the constant term of our transfer function in the denominator. This meant that 9Ks was equal to Wn squared. This gave us a value of omega n equals 11, which gave us a value of Ks equals 13.45.
After doing the calculations, we plugged our KT and KS values back into our transfer function and graphed on MATLAB utilizing a step response. As you can see here, our x-axis is still in time in seconds. Notice that it is up to a 1/9 of 1 second, while our y-axis represents the amplitude, going in a decimal value up to 1. From our graph, we can see that we have a settling time of about 0.55 seconds, which, as you can remember from our calculations, we wanted a desired settling time of 0.5 seconds. So our result with our transfer function was actually very close to what we had calculated. Using our KT and KS values in our transfer function, the top graph represents the magnitude still in decibels. As you can see, we still have a negative magnitude, which did not change from our original with no KT and KS values. Below that, though, is our phase graph, which is still in degrees, and from the graph we can see that there is more of a rise in the middle of our graph than before when it settled out and then still went negative. This is to do with our new calculated KT and KS values in the transfer function.
Next we have the steady state error calculations. The steady state error is calculated by taking the limit as s goes to 0 of s times 1 over 1 plus g of s times 1 over s. G of s is the transfer function of our system with the disturbance without respect to our input or output. This equation gave us a steady state error of negative 9 Ks. This gave us a much higher error than we wanted of about 121. So we decided that we had to change our settling time or rise time to get a new Ks value to fix our error. In order to fix our steady state error, we needed a better value for Ks. To do this, we decided to change our rise time from 0.2 seconds to 1 second. Our new value for omega n became 2.2, and our new value for Ks became 0.538. This gave us a steady state error of 4.5. We then plugged in our omega n value to the other equation to find our dampening coefficient, which gave us a zeta equals 4.18.
From finding our new Ks value, we had to find a new steady state error, which was calculated to be roughly 4.8. Using this new Ks value back into our transfer function, we plotted it in MATLAB and got a step response that we cannot explain. As you can see from the graph, our step response has a settling time of roughly 12 seconds. Even though we did not change our settling time value, and we only changed our rise time. Using our omega n value, trying to plug that back into our settling time calculation to find a new settling time, we were not able to find a new value. So we used our original settling time of 0.5 seconds. We were unable to get our system to respond how we were calculating. Here we can see our new Bode plot for our new Ks value. On the top you see a magnitude still in decibels with a very good response. Beneath it we have our phase in degrees still, And as you can see, there is no longer the spike in the middle. Now we still start high, go down, level out for a little bit, and then end in our frequency still in radians per second. In conclusion, having to calculate our new Ks value to have a good steady state air value, we were left with a bad step response, but we had a very good Bode plot for both phase and magnitude responses. Also, we noted that from all of our step response calculations, none contained any overshoot, which is a very good thing. Also, we did note that increasing the rise time led to a decrease in steady state air because of the relation from our transfer function to respect of the Ks values. As best as we can tell, our system seems to be stable by looking at the Bode plot and step response. But we did note that our system was not realistic for an airplane control surface, because as you can imagine, that with a plane control surface, you need a very rapid response, which our control system was not found to be able to do without losing stability.
And that concludes our presentation of our control system analysis final for fall 2014. Thank you for viewing our presentation.